Good afternoon, everybody. It's a great pleasure to have Professor Shing-Tung Yao here giving a talk. Let me just say that Professor Yao really needs very little introduction, okay? And it's nevertheless a great pleasure to say something about Professor Yao, especially since I actually view Professor Yao as one of my advisors because I was a graduate student at Harvard when he was there, and I've been knocking on his door quite often, I would say. So he also wrote a letter of recommendation for me after my graduation, so I was able to get a job. I'm pretty sure that he wrote something very nice about me. Okay, so anyway, I was at his 70th birthday gala just maybe a month ago, and to my delight, I discovered his birthday. The date is, we're in the same month, okay? So, of course, he looks a little younger than I am, okay? So it's hard for me to actually think he's not in his 50s, given his energy and, you know, all the things he does, okay? So, the Professor Yao, as we know, is one of the very best mathematicians in the world, and his groundbreaking work on Calabi conjecture, along with many other outstanding work, had earned him the Fields Medal, which of course in our world supersedes every other honors he had received. But I will mention a few others. For instance, even before the Fields Medal, he was a MacArthur Fellow, and he also had the US National Medal of Science and the Wolf Prize. All these are very, very prestigious honor, okay? And I actually noticed that Professor Yao had a long list of honorary degrees, okay? None of them actually mattered except one. He actually received an honorary doctorate degree from HKUST in 2004, okay? So, Lionel, you must remember this, right? Yeah. So, I myself, I mean, you know, as I said, I began my PhD study at Harvard in 1983, so shortly after Professor Yao came, so I can say a little bit. Apparently, he was on Harvard radar for a long, long time, and Professor Yao at the time was in San Diego. He really enjoyed his, you know, the climate and everything. I mean, it was just, of course, who wouldn't want to live in San Diego, okay? However, according to my advisor, okay, David Mumford, he finally decided to join Harvard because he was he was a big promoter and of trying to engage of mathematics in China and try to engage mathematicians, especially consider that time the Chinese mathematical community is relatively weak, okay, in terms of modern mathematics. So Professor Yao has spent so much time and energy trying to bring mathematicians from China to visit and also to nurture young mathematicians in China. And according to my advisor, when Barry Mazur at the time, who was the department head at the time at Harvard, went to him for the nth time, he finally decided to join Harvard because he was tired of taking people to the San Diego Zoo. Okay, so that was the story. I don't know whether it was true, okay? So anyway, actually, I mean, on the side note, that was also the time I actually got to know Andy, by the way. We were, you know, also, he was a fellow and I was a graduate student. Since Professor Yao joined the Harvard Math Department, before that, I was one of the two graduate students from mainland at the time. There were very, very few mainland students. This was 1883. And since he joined, suddenly there was a big surge of graduate students from mainland China. and many of whom I actually knew. One of them was my classmate. So from that point on, you could already see how much Professor Yao has done to nurture the Chinese mathematics community. Okay, so this was, I can, speaking for many others, for my, obviously, many of my friends in the community, that I don't believe anyone has done more to help developing mathematics and nurture talents in mathematics in the Greater China area than Professor Yao. Okay, so this is, I'm quite confident. And also, a couple of, also another thing that's overlooked, I think most of us have known Professor Yao as one of the very best pure mathematicians in the world. However, he actually, especially in the last, I would say 10 years, maybe 10, 15 years, Professor Yao has always been a relentless promoter of applied math and trying to help developing applied math in Asia, especially in Greater China area, in the US as well, and the nurturing talents. Actually, many of his students are top, really top researchers in applied math, okay? So finally, let me just give a little bit of anecdotes. I think it's very well known that Professor Yao is one of the best fundraisers in mathematics, okay? So I don't believe there is any mathematician even remotely close to what he has done in terms of fundraising. And this, to me, that was not a big surprise at all. I remember going to one of his parties when I was a graduate student in his house. And then when I walk in, Professor Yao immediately said, well, today we're going to play the game of Monopoly. Okay? I don't know how many of you have played the game Monopoly. You're given some money, then you go around, then you have to determine whether you buy a house, you want to get out of jail, and all these things. You have to trade, right? So I soon lost all my money to him. And in the end, he took money from everybody in that particular game. So with a few very savvy moves. So that was the time I realized, he was actually very, very good at fundraising, okay, or fund getting. So now, okay, so without further ado, let's give Professor Yao a big welcome.
Okay, thank you very much for the invitation, and it's a good honor to come back to HKSTU after many years. So I was honored to have the degree here, and I hope I can do more for you. Anyway, today I'm going to talk about an interesting history about general relativity and gauge theory, which I think could be controversial to my friends in physics because they think completely differently. But nevertheless, what I said actually is well documented. So in any case, I'm talking about the subject majorly because I think it's important for mathematicians to understand the origin, which they will know better how to work in this subject. So let's start out by saying Einstein, of course, is a founder of all these things. By 1905, special relativity is well understood up to a large extent. But there's a contradiction between special relativity and Newton's theory of gravity, because one assumed information cannot travel faster than light, but Newton's gravity is action at a distance, is instantaneous. So it becomes a huge problem for him to try to see how to resolve the inconsistency between these two important subjects, which is well accepted at that time. So it is a very daunting task, and it is finally accomplished in 1915. And many physicists up to now say that this is probably the most creative work in science in the history of mankind. But there are many history which is not well understood by people, even by great experts, I think. So let's just start out from the major, very fundamental principle that general relativity was built on. It is the concept of equivalence principle. The development of this has led to a long history. You see this diagram a lot in many popular science books. Elevators, where Einstein was playing the thought experiment about going up and down, accelerating the frame, namely how people feel inside and all that. But of course, this went back long, long ago, even before Galileo. But actually, it's a famous experiment you learn in high school. It's showing the acceleration of a test mass due to gravity is independent of the amount of mass that's being accelerated. And he did a famous experiment in the Tower of Pisa, where he threw a big ball and a small ball down, arrive at the ground at the same time. So this is a famous experiment. In between, a lot of people look at this famous question of equivalence principle, and Kepler and many other people did it. I don't have time to look into it. But Einstein said in 1907, we assume the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system. So the gravitational motion of a small test body depends only on its initial position in space-time and velocity, and not on its constitution. So the outcome of any local experiment in a freely falling laboratory is independent of the velocity of the laboratory and its location in space-time. So this is one of the most fundamental principles that Einstein tried to build his theory of gravity. And without that, the whole Einstein theory would not work. So that's why I said at the very beginning. So he wanted to develop such a theory where the laws of gravity should be independent of observer. But it's easy to say, and that's what Einstein himself said. I will show you what he said himself. It's easy to say, talk about philosophy, but in reality, how do you build such a theory? That's the question. But it's important to realize that gravity is equivalent to the acceleration of the reference system, and the acceleration of a particle can be described by the curvature of its trajectory. And that's how we know the mass and many things of a particle. And Einstein started to speculate that the new theory of gravity should have something to do with a new concept of space. And he knew that the static space is not adequate, which means you fix an observer, namely a fixed coordinate system. So little did people talk about this, but the great work benefited from help of many geometers, including his friend, college friend, Graustein, and also his teacher, Minkowski, and also Hilbert and Noether. All this has contributed a great deal to the development of general relativity, which most physicists would not acknowledge. But it's there, then I want to talk about it. But most important of all is actually Riemann. Riemann wrote a very famous thesis in 1854, one of the greatest men in the history of mathematics, I would say. He only worked in mathematics for about 15 years. He died when he was 39. And he started work in 1854 and finished in 1865. But in between, he created almost every modern subjects that we see today. And Riemann, before Riemann, the concept of space is very different from what we see nowadays. There are only 3 types of space that we care about: the Euclidean space, the sphere, and the hyperbolic space, which was invented by several people, including his teacher, Gauss. And, but all these ones, basically, you can put in one coordinate system. You know exactly how to describe them in detail without any problem. And so that's why the universe, as using one coordinate system, is basically static. That's what Newton did. In Newton's gravity, the whole universe is static. But Riemann now understands that it should be different. The notion of space was invented by him, the modern notion of space. Before that, we don't know how to describe a space in a very intrinsic and important manner that is dynamical. So he invented a space without referring to a fixed coordinate system. So, coordinate system is a great invention due to Descartes. And once we know coordinate system, we know how to describe many things using algebra or other things, but at least it's important. And he knew that when 2 points are getting close, we should feel a first-order effect. It looks like Euclidean space. But then when you count a second-order effect, it should give some curvature. And that's how curvature is coming into description of space. So Riemann describes a space which is dynamical and also shows the influence of curvature. He wants the space that we see as a space-time to allow many different observers. On the other hand, he said the essence of the thing that we see in physics should be independent of the observers. And the observers can propagate information from one to another. Now, you may say that you are just BS. Riemann was just thinking abstract mathematics. But in fact, that's the reason you think in that way is because you never read Riemann's paper. Riemann wrote this paper for the sake of physics, not for geometry. He said we should look at nature in the following way. Nature means physics to him, and we describe it in the following way. So he actually was thinking in terms of physics. He wanted to use a variety of different coordinate systems to observe the basic properties of space. And he wanted to find those which is independent of the coordinate system. Which means what? Which means that he is using the crucial principle equivalence already in constructing the basic geometry of Riemann. It's called Riemannian geometry. Okay? Should be independent of that. And he defined the concept of curvature already in the very beginning. And this later, of course, becomes extremely important for Einstein's general relativity, including curvature becomes the gravitational content, and material distribution in Einstein's theory is part of the curvature. So the distribution of matter will change over time, and so does the curvature. And this, as a result, creates the concept of vibrational space-time. And because of that, Einstein comes to the conclusion that there's a gravitational wave. Although it's very small, it still be there. And this was observed a few years ago directly, but although it's indirectly, it was known for a long time. And when Riemann developed this, it's very interesting. As I said, he's thinking in terms of physics, not in terms of geometry. He said the smallest and the greatest part of space should be described in a different way. This is a very remarkable concept because in 1854, he already knows that very tiny part of space should be different from the global part of space, which nowadays you would say the very tiny part corresponds to quantum physics, and the large part corresponds to cosmology, and they are very different. And we want to understand how to contact them in a very serious manner. And Riemann actually challenged the reader to understand this connection. Of course, this is a concept which is unknown up to now. Now, Riemann started his scientific publication in 25, as I said, but he died when he was 39 because of lung disease. He got TB. And during those last 3 years before he died, he spent his time in Italy. And he had several followers in Italy and Switzerland. So an important person is Christopher. And then Richard, and then Larry Tutor. They were not exactly in the same contemporary, actually, but they were influenced by him, by his mere presence. So Christopher and Richard and all this are basically explain what is known to Riemann. Riemann did not publish all his papers. He has these disciples trying to understand what he did. So Christopher invented Christopher symbol, which is extremely important for later, for general relativity and also for gauge theory, which I'm talking today. And Richard invented something called Richard curvature, which is the important part of Einstein equation. So they basically generalize and do what Riemann knows. And most important one is the understanding of tensor. Tensor was already known to Riemann because he invented the curvature tensor. He wrote down. But he knew it, and not everybody knew it. This in 1854. But this tensor becomes the most important concept later. Up to now, not only in physics, but also in combinatorics. Nowadays, people in combinatorics talk about tensor calculus also. So Einstein, in 1934, wrote a paper. This paper was really cooked by people in physics. I don't know why, but this was written by him in 1934, describing exactly what he sees, the development of general relativity. So it cannot be wrong. It was written by himself in 1934. So he described the history himself. This is according to his own writing, basically. I just summarized what he did because I cannot quote the whole paper. He said the first stage, of course, is special field of relativity. And of course, they're including great men like, besides himself, Lorentz and Poincaré. And then he realized, of course, the velocity, when the velocity is close to light, then the measurement distance is affected by time and all this. And he realized there's a contradiction, inconsistent between Newton's theory of gravity is incompatible with special field of relativity invented at that time. So at that time, Einstein has no idea what has been done by Riemann, because Riemann's theory, although has been there for almost 60 or 70 years, but he has no idea. So at the beginning, they were trying to collect Newton's gravitational theory was 3-dimensional, just change it according to special relativity. If you hope that you can change it so that it will be good enough. But this let Einstein completely go astray for a few years. He has no idea what's going on, what to do. This is what he said in his note. He said, I was, of course, acquainted with Max Wheel, the Greek philosopher. Everybody said that Einstein's theory was influenced by him. He said, this is good, and I know it. But there was something fascinating about this idea to me. He said, that's great, but it provides no workable base for the new theory. He said, you talk and talk, but I need to put it in an equation, something that I can do calculation. And Max philosophy gave you nothing. So he has to develop something. He said, okay, I try to understand gravity according to Newton. So the simplest thing was to take Laplacian of a scalar potential of gravity. This is what he wrote. And this is what Newton's theory says. Newton's theory of gravity says that you have a potential, you take Laplacian potential equal to the matter distribution. That was simple and clean and good. And this is called the equation Poisson equation, we call it in mathematical term. So he said, okay, why don't we just do it? And then we just do it, but differentiate with respect to time just similar to what special field of relativity would be happy with. And the law of motion and mass point in the gravitational field could also be adapted to the special field of relativity. Well, this seems good, but then he said there's back reaction. And this is going to create a lot of problem in order to be compatible with principal equivalence. So he has to abandon it. So he has to give that up, the obvious generalization of Newton's theory by just changing the equation suitably. So he said in a very clear manner, the principal equality of inertia and gravitational mass, which is part of the principal equivalence, could now be reformulated quite clearly as follows. He said in a homogeneous gravitational field, all motions take place in the same way as is in the absence of gravitational field in relation to a uniformly accelerated coordinate system. So the important thing is that the coordinate system should be accelerated. That means their velocity changing. And this creates all the problems he has to face to deal with equivalence principle and to deal with general relativity. So that accelerated coordinate system means in the case of the elevator is accelerated. And he has to deal with that problem. So he said if this principle held good for any events whatever, this indication that the principle of relativity needs to be extended to coordinate system in non-uniform motion with respect to each other. So the important thing is that coordinate systems are changing in a non-uniform manner. And you have to create a gravitational field to be happy, to be consistent with that. So every law has to be consistent when you change the coordinate system from one to another with making the motion to be non-uniform motion. And this was important when in 1908, many people did not cite this, which I think is too bad. So when Einstein was a student in Zurich, he was in ETH. He has a professor, he has a teacher, was Minkowski. Minkowski is one of the greatest mathematicians by the end of 19th century and the beginning of 20th century. So many people did not realize that Einstein actually is one of the best mathematicians who taught him. That's Minkowski. And Minkowski even said there was a lazy student in my class who had recently done an important work. Why he's lazy? Because he did not show up in class. He got his friend Graustein to hand in homework for him. He did not do the homework either. So this is what happens. Why he said, but he did have a great teacher. He said he recently did a great work, means special relativity. And Minkowski said that now I come up with a geometric interpretation of this work of special relativity. So Minkowski actually studied physics also by several great physicists at the end of 19th century. So it's not that he didn't know physics. In those days, before 19th century, before early 20th century, every mathematician knows physics. This is something you should know. Both Gauss, Riemann, Hilbert, and all this has made serious contribution to physics. Gauss and Riemann actually has contributed 3 of the Maxwell equations in physics. So anyway, so Minkowski then said that he established harmony between math and nature should be there. So geometry should be an insight, key to physical insight. So he ascribed physical reality to the geometry of space-time. It's not Einstein who did it, it was Minkowski who started this concept. He said the reality should be geometry of space-time. And this was given by Minkowski in a lecture in 1908, September 21st. And the title, Space and Time, was first time given by Minkowski. And everybody said that it's due to Einstein, but it was Minkowski who started to call space-time, no other people. And you see what he says. This statement was usually attributed to Einstein, but it's due to Minkowski. He said, the views of space and time which I wish to lay before you has sprung from the soil of experimental physics. He said, what I'm saying is so fundamental because it comes from experiment. And therefore, the strength of his view is completely radical, and it should be important. He said, henceforth, space by itself and time by itself are doomed to fade away into mere shadows. So space and time cannot exist by itself anymore. And only a kind of union of the two will preserve an independent reality. So this is what he declared. Now, of course, Minkowski do not say it based on no reason, and he actually create such a concept to make you understood. In a way, everybody's work depends on previous people's work. Many physicists do not realize too. Poincaré in 1906 observed a simple thing. He said, suppose we change in the group or Lorentzian transformation, you will change time to imaginary time. You replace t by it. Then the Lorentzian group becomes the Poincaré group, becomes rotations. And he said it's amusing and it's important, but he didn't know what to do yet. And then Minkowski changed it in a very clear manner and applied this idea to form the Minkowski spacetime, which I will discuss a little bit later. But even after Minkowski discussed it, Poincaré still thinks that four-dimensional spacetime is not physical. He declared that the language of three dimensions still seems to better fit to our description of world. Although this, so he still feels differently. Even a great man like Poincaré in 1908, after Minkowski pointed out, he still did not believe spacetime should be more conveniently, and actually more than conveniently, in the utmost importantly described by four dimensions. He said the world in space and time in a certain sense is a four-dimensional, non-Euclidean manifold. In truth, we are dealing with more than merely a new conception of space and time. The claim is that it is rather a quite special, specific natural law, which because of its importance, since it alone deals with the primitive concept of all natural language, namely space and time, can claim to be the first of all laws of nature. So he said the concept of space-time together is the first of all laws of nature before anything. So that's what Minkowski said. So what happens is that in 1908, Minkowski constructed four-dimensional space-time. He introduced a metric tensor following Riemann's work, that's why I mentioned Riemann, to give a completely geometric meaning of special relativity. And the Lorentzian group, which is so fundamental for special relativity, becomes the group of isometry of this space-time of Minkowski. So Minkowski, in this year, created the most fundamental concept of general relativity, which many people ignore. In fact, I studied general relativity for 40 years. The first time when I watched Minkowski's space-time, I thought this was rather trivial, why it's called Minkowski space-time. Only after thinking about history, I realized how important the breakthrough is. Namely, people start to realize that we are dealing with four-dimensional space-time, no more three-dimensional. So we now know that we learned the space, that we are living in a four-dimensional space-time. And Einstein, I think, got the most important inspiration for general relativity this year. He knows that he has to deal with four-dimensional space-time, not three-dimensional. Now, many people knew that Einstein said in this year that 1908 is the most inspiration year for him, and many people thought that it was due to the thought experiment Einstein did because of the accelerator talking back and forth. But I think they are wrong. I think Einstein considered this year to be most inspired year for him is because the understanding of four-dimensional space-time. Just imagine the concept of three-dimensional, which has been held for 2,000 years or 3,000 years, now suddenly changed to four-dimensional. The static space of Newtonian gravity is no more adequate immediately once you know you need to go to four-dimensional. And you have to understand that if you do not have such a conceptual breakthrough to go from three-dimensional to four-dimensional, there's not enough room to show its dynamic nature. Three-dimensional has no way to show dynamics of gravity. Only in four-dimensional space-time come up and you can show the dynamical nature. So only after that, Newton's theory of gravity being static is no more there. Only after this we know it has to be four-dimensional. Now, it's more important than just the conceptual breakthrough. The important thing is that only after we go to four-dimensional that we know we have to use a new concept to describe gravity. What is a new concept? We need to use a tensor to describe gravity. Newtonian mechanics use a scalar function, and physicists do not know what a tensor means at that time. Actually, not only physicists do not know, most geometry do not know what a tensor is, because Riemannian geometry was not that popular at that time. People were still calculating something standard. Only after Minkowski, you have a tensor, and he perfectly described the special field of relativity. Einstein now knows that he should go to a tensor instead of a scalar function. So this is extremely important, major breakthrough technically. Because you stick yourself to scalar, you will never work out anything. You don't have enough freedom to do it. Now, Einstein needs to know, in order to combine Newtonian mechanics with Minkowski spacetime, so he knows infinitesimally his theory must reflect Minkowski spacetime. That's because when things are very close to the first order, the gravitation law should be Minkowski spacetime. But when second order effect of gravity comes in, some curvature becomes important. So he needs to know how to calculate curvature now. At the time, as I said, nobody knows much about tensor, even geometers. But on the other hand, Einstein knew that is right, because he knew that in special relativity, everything depends on the velocity vector where you travel. If you travel along the velocity vector, and when the velocity is close to light speed, the concept of distance and all that changes. But if the observer is in a direction orthogonal to velocity, then it's different. So he knew that some kind of concept has to be created, namely a quantity independent of depending on the direction and the point. He didn't know what that is. He asked his friend, Marshall Grossman, to look it up for him. So Grossman was reluctant at the beginning, but he found out that the tensor is the right concept for him to use. So they start to use tensor. Now, at this point, one knows that at every point it should be approximated first order by the Minkowski tensor, which was created by Minkowski. And Grossman, on the other hand, as I said, he helps Einstein to do the homework and all that. He reluctantly go to the library and found out such a thing, tensor. And this is very happy for him, because now they found a concept which satisfies the equivalence principle. You want to find something, entities, which independent of choice of coordinate. And tensor was created just for that purpose. And then you want to differentiate it. Because in Newton's theory, you have to differentiate the scalar function. And so you have to differentiate the tensor also. So then they realized that there's some connection theory of Christopher and Levi-Childa. And it was invented before them. So they were lucky such things were invented. Now this whole theory here, I will mention to you later by Einstein himself. He credited this important contribution. So this was the first question that he said. We have a tensor, what do we do? And so then second question, he said, is how to generalize Newton's law of gravity in this new framework. And so the Newton's equation is simple, actually. It's a second differentiation of the potential is equal to matter density. He said, now, what do we do? We want to generalize this concept of Newton, and we want to create that. So at that time, neither Einstein nor Grossman knows how to defend such a thing. So Grossman was actually reluctant to do it, and then Einstein requested him, so he went to find out Richard's paper. There's a paper by Richard and Christopher and Levi-Childa in 1900. There's a long paper, 100 pages long paper, many chapters. So Grossman was very happy when he read chapter 6 of that paper. He found out Richard has found the Riemann's curvature tensor, which is a rather complicated tensor. He made it with second order tensor, second degree. And this guy happens with same degree as a metric tensor. And also it can be regarded as a second differentiation of the metric tensor. And this is extremely good because Einstein realized this exact analog with the Einstein equation, with the Newton's equation. You differentiate the potential, which is now considered a symmetric tensor. You differentiate twice, and it becomes like Ricci curvature, and you can set it to be equal to the metatensor. And metatensor is now understood quite well by that time. It's called the metatensor on the right-hand side. The equation was written down by Einstein and Graustein in 1912 and 1913. It's in the bottom. Rij is a Ricci tensor, and the right-hand side is Tij. So this equation was written down and was important. And now, it's interesting. Einstein tried to solve this equation by the post-Newtonian approach. And he did not recover the famous gap in understand the Mercury's perihelium sieve. And he gave up. And he felt very frustrated. Now, actually, very few physicists know that. And everybody accept that this was a fail because they did wrong equation, then didn't come out with the right equation. But actually, just for this purpose, for this experiment, the equation that Einstein and Graustein wrote was right. Because they are dealing with the case in vacuum. The metatensor equals 0. In the case of metatensor equals 0, the equation written by Graustein and Einstein was actually correct. So there's something wrong. Namely, Einstein actually did a computation which is wrong. Now, actually, I do not find any people, historians in the last 100 years, to notice that the computation must be wrong. He did a numerical calculation, which turns out to be wrong. And I think it's very instructive to actually do this calculation, to find out exactly what he did wrong. This is an interesting question. I think historians should look at this. So the equation was actually right in this special case, but the equation was wrong for general case. But in this case, it was actually right. And Einstein did it wrong. This means that approximation method in general could be wrong. And numerically, numerical analysis could be wrong in many, many cases. And we have to be very careful. Now, then you try to use special coordinate, and this doesn't work. And despite the many communications between him with a very great differential geometer, Relativity, didn't work out. So now before I go on, let me just tell you what Einstein himself said, okay? He wanted to include nonlinear transformation historically, and he said it could no longer be required coordinate difference to signify direct results measurement and all that. And it took a long time to see what coordinate at all mean to him until in 1912. That's what I just said. And then he found out the law of inertia has to be built in a very careful way. I don't want to spend too much time on this. And he knew that some metric tensor has to come in, dx squared. And this was trying to be compatible with what Minkowski do. And this is what he said here. And he certainly knows Minkowski's work, and it's important. So he said the line element of Minkowski has to come in. Now, let me not go through too much discussion here. And so this is how he motivates himself to get the metric tensor to come in this way. And these are all the statements he mentioned, how he come up with this. But at the end, let me see what his quotation. He said these are two major questions he has to address. This Einstein's own writing. He said the first question is that if a field law is expressed in terms of special theory of relativity, how can it be transferred to the case of Riemann metric? And then the second one is that what are the differential laws which determine the Riemann metric itself? These are two major questions that Einstein asked himself. And then he said the problem two was required the construction of the differential invariance of second order, and this was established by Riemann. So this is his own admission. He learned this whole thing from Riemann, the tensor of curvature. And also, he said, well, we had already considered the right field equation of gravitation 2 years before the publication of general theory, but we were unable to see how they could be used in physics. So this got him very frustrated because he did something wrong. And in fact, he struggled from 1913 to 1915, and he still did not get anything right. Actually, finally, in 1916, half a year after the equation was written down, the equation was solved by Schwarzschild. So there's no more debate or numerical calculation mistake. But only after Schwarzschild, one knows exactly the experiment is actually right. Now, it's interesting, as I said, Einstein got discouraged when his approximation did not give him the right answer. Compared to physical observation, he got very depressed. And he said that, I feel sure that they could not do justice to experiment, to experience, and he started to try to fix coordinate system, and he got something wrong, and he was really frustrated. Only after 2 years, he finally returned to the equivalence principle and did the Riemannian curvature. And then he claimed he succeeded to do that. Actually, I believe that he also made a mistake, which historians never realized. But anyway, I'll talk about it a little bit later. But he said, all this, actually, the happy achievement seems almost a matter of course. And any intelligent student can grasp it without too much trouble. So he said, after finishing the equation general relativity, he said, actually, the whole thing is trivial. It's rather clear. Any graduate student could do it. But on the other hand, the years of exhaustion, answer searching in the dark with the intense logic, has really driven him crazy, but now he finally is verified. That's what he said himself. Now, let's go back to what happened in the final stage of Einstein's work in general relativity. In the last year, namely 1915. In the spring of 1915, it's well known, he visited Hilbert in Göttingen. He was in ETH in Switzerland. He visited Hilbert. He asked Hilbert what to do with the equation. Hilbert, of course, is a great geometer, and he's a founder of modern geometric invariant theory, as any mathematician would know. And he gathered a large group of outstanding mathematicians in Göttingen. Some of them are relevant people are here. Friedrich-Klein, who is also a great man in understanding how to use symmetry group to classify geometry. Now, this is also to the contradiction to many physicists who thought this concept was created by Einstein. But Friedrich-Klein actually started this whole thing in 1870 to use symmetry group to classify geometry to create equations. And then Hermann Weyl, who was a student of Hilbert, was there. He was a founder of gauge field theory, which I will discuss. Now, when Einstein visited Göttingen in the spring of 1915, Hilbert actually asked Emmy Noether to visit him in Göttingen. She is the greatest female mathematician in history of mankind, Emmy Noether. So she came. She was not considered important because women were not allowed to be, be professor in those days. And Hilbert and Einstein actually tried to help her a lot. We should know that during this period, Noether was asked by Hilbert to start to develop the famous theory of current, which now people call it Noether current. He used a group of continuous symmetry to deduce the equation of motion. And in general relativity, continuous group of symmetry is a group of coordinate transformation. And actually, I think Noether suggests to Hilbert to use the action principle. The Hilbert action was no question due to Hilbert only, not by Einstein, because Einstein has no trace to have ever written down anything related to action. And I think Einstein has never used action principle in gravity in his whole life. And the action principle was done, and this was in November. And actually, at the end of the summer, Hilbert wrote a letter to Einstein saying that he found the equation. And Einstein refused to visit Göttingen because he wanted to claim his credit. And he started to give 2 weeks lecture in the academy, and he did not know what to do because he still could not find the right equation. It was Einstein who asked Hilbert to send him a postcard about what the equation looks like. So Einstein actually quickly got the equation, and based on this equation, he deduced the astronomical calculation that I just mentioned. Now, this is a famous story, and I think at the beginning, Einstein was extremely unhappy about Hilbert's priority, but Hilbert quickly declared that the work should completely belong to Einstein, and they become good friends again. I believe this is a fair statement that Einstein did the most important work conceptually to the end. But the fact that all these Greek geometers has not been credited by the physicists is not terribly fair. Especially Hilbert's action of principle for this. Now, looking backward, that's what I suggest some people in the audience may be interested to do. The correct equation of motion derived by Hilbert and Einstein could have been found by Graustein and Einstein in 1913. The left-hand side is an equation consists of Ricci tensor. And the left-hand side does not satisfy conservation law, but the right-hand side does satisfy conservation law. So the equation clearly cannot be right. And somehow Einstein did not realize it, and Graustein did not realize it. And the interesting thing is that the left-hand side, nowadays we call the Einstein tensor, was actually written down by Ricci. Ricci and Levi in the famous paper in 1900 actually wrote down Rij minus R over 2 Gij. This was in chapter 7 of that paper, which Graustein did not read further because he found the Ricci tensor in chapter 6 and he is happy enough, and then he dropped the rest. But he go one more chapter, he will find the actual tensor. But anyway, that's life. And so this is the right equation, and as I said, Ricci actually know the left-hand side satisfies the conservation law by using Bianchi identity. So if Einstein and Graustein trust the beauty of geometry, he probably would have found the equation. But in any case, he did not do it. That's interesting enough in the following sense. When Einstein found the right equation, and he did the calculation right in that case, but as I said, it's the same equation. Namely, if Tij equals 0, that's what he is doing. He did two calculations, one in 1913, one in 1915. He's using the same equation because R equals 0. And yet, in one time, he got the answer right, namely in 1915. In 1913, he got the answer wrong. So what does that mean? That means at least one calculation that he did was wrong. Mathematical logic. But I actually suspect he probably did both wrong. And he was correct by Schwarzschild after half a year. But this is my speculation. But in terms of mathematical logic, at least one calculation was wrong. Because it's the same equation. Okay? So it's a very interesting history that one will find out. But anyway, one should know that Einstein equation is now established, but there's no global symmetry of this whole dynamics. It's changing dynamically. It has been very successful in the last 100 years, but there are many problems. Einstein, at the beginning, thought that now I solve everything. Everything is just a matter of triviality for mathematician to do the calculation, and we are finished in terms of gravity, beautiful interpretation. But he forgot that many important things has not been done. Namely, there's no more global symmetry. Many of the important things that in Newtonian mechanics are not there anymore. And you cannot define linear momentum, you cannot define mass and all that, because continuous symmetry does not exist. You cannot define angular momentum, or all this needs to be understood. So this concept of energy has become an important problem for a long, long time, until recently even. And now, so Penrose and Hawking was worrying about this a long time ago, 45 years ago, and they were interested in this, and this was finally achieved by quite a few mathematicians here that I mentioned here. Once Einstein knew the equation is good, and Eddington has done the famous observation, which proved Einstein was right. Einstein becomes extremely famous by 1918 or so, and everybody was excited about this whole thing. And then Einstein wanted to derive many important things out of the Einstein equation. An important thing that people were worried about at that time was how to merge gravity with electromagnetism. At that point, that was the major matter, electromagnetism. Several mathematicians immediately took the task to merge gravity with electromagnetism. This is a very important period of time that mathematicians, geometers involved in this whole subject. So he had extensive communications. Einstein's letter is all appear now. In the old days, it's not. You can find it yourself. He has extensive communication with Levi-Civitar and Cartan, Elie Cartan. In 1917, because of this motivation that Einstein wants to merge electromagnetism with gravity, Levi-Civitar realized that, okay, there's a Lorentzian metric. It creates a concept of parallelism of tiny matters. And he said, well, the concept of parallelism alone retains most properties that we are interested in curvature. See, you move a vector around in a parallel manner, it comes back, it may be different angle. This was already observed by mathematicians for a long, long time. That's 100 years ago. Physicists only worried about it about 1960s, actually. This is a famous experiment which I will mention. So Levi-Civitar said, okay, let's say we can forget about metric. We just care about parallelism. Now, parallelism is actually dictated by crystal symbol, which I mentioned earlier. And Levi-Civitar said, okay, why don't we just look at crystal symbol as an independent variable? Metric, kick it out. Let's just use crystal symbol. So that's fine. And then he said, once you do that, there are too many redundant degrees of freedom, and it's no good. And so we have to get rid of this redundancy by using some transformation, which we now call gauge transformation. So this, from geometric point of view, this is the first time we look at gauge transformation. And then Hermann Weyl in 1919 also attempts to unify Maxwell equation on electricity and magnetism with Einstein equation on gravity. And he observed the Maxwell equation exhibits similar gauge dependency as in the theory of Levi-Civitar we just mentioned. So Levi-Civitar was talking about crystal symbol, parallel transportation, and there's gauge dependency, and he observed that it's similar to what Maxwell equation had. Then he started to say that minimal physical quantities, such action that appears in theory, should be independent of choice of coordinate system and also independent of choice of gauge. Now, this is a very important concept that Hermann Weyl established. This is a gauge principle, that gauge invariant principles. This is very important for them. And this theory, which he called gauge theory, what he did, at the point, he was trying to use conformal transformation of some sort. So he used the group, gauge group, what we call gauge group, to be multiplicative real numbers. And this theory actually pleasing Einstein. Einstein was very pleased by this work, what Hermann Weyl. He said it's a beautiful theory, but it's not physical, he said, because in this theory, parallelism does not preserve length. So this was in 1919. And then it was big until quantum mechanics started to flourish. This was due to London and several other quantum physicists. I mean, Schrödinger probably has a hand on it. He proposed a quantum mechanical interpretation of Hermann Weyl's theory by replacing the group of real multiplicative number by the circle group. Why the circle comes in? Because the phase that comes in. And this phase has been used in a fundamental way in understanding the wave function for quantum mechanics. And so immediately, Hermann Weyl wrote in his famous book, it's about group theory in quantum mechanics, he said this principle of gauge invariance is quite analogous to the previous setup by the author, which he did in 1919. And then he said, now I believe that gauge invariance does not tie together electricity and gravitation. He said it should be rather electricity and matter. So already, by that time, Hermann Weyl already realized that the gauge principle is more relevant to matter and electricity, not quite gravity yet. Although there's an analog, namely the coordinate transformation, but he looked at the gauge invariance to be important. It's this principle of Hermann Weyl on gauge invariance that we know how to derive the field strength for the gauge field, and the action is the integral of the field strength. So this is well known in Hermann Weyl's book, and now you can write down the equation of motion for matters. So it turns out Hermann Weyl's theory of gauge invariant principle has influenced physics all the way up to nowadays, including mathematics, of course. And in 1956, Hermann Weyl wrote, actually 1955, in a conference dedicated to his birthday, I think, and he died right afterwards. He wrote, the strongest argument for my theory seems to be this, that gauge invariance was related to conservation of electric charge in the same way as coordinate invariance was related to conservation of energy and momentum. This was written by Hermann Weyl without knowing any work by physicists. It was written by him. Well, he is close to death at this year. But many people, especially physicists, did not realize already mathematicians led by Elie Cartan in 1926 already generalized the idea of relativity and proposed to develop parallel transposition not only for tangent matter, but also for vectors in a fiber bundle. The concept of fiber bundle was invented by Whitney around that time, and Elie Cartan immediately tried to generalize it. So basically, you can say that this theory, Hermann Weyl, has been generalized to non-abelian gauge theory already by 1926, because he knew how to do this curvature, transportation, and all this already by that time. All these works I mentioned should be recorded in 1950 by the famous paper of Chern in his plenary talk in the International Congress of Mathematics held in Harvard University in 1950. I suggest you take a look at this paper. It's a full discussion about differential geometry of fiber bundle, where he discussed how to do covariant differentiation, how to define curvature, and how to define Chern classes, Pontryagin classes, in full great detail. And it's exactly the modern point of view of what a fiber bundle and differentiation would be. So actually, well, this is Chern's account in 1950. But actually, the years before 1926, where Cartan wrote his paper, to 1945, there were extensive development of non-abelian gauge theory due to Whitney. Whitney, in his famous work, actually this was only a lecture exposition of what he did. He did it in 1920s and 1930s when he developed his immersion theory. And then Stiefel actually followed him, developed something called Stiefel-Whitney classes. It's a mod 2 classes. And then Pontryagin in 1941, actually, this was published, this must be 1949, it's wrong, it's 1941. Published his famous work on Pontryagin classes in 1941. There's a mistake there. And then Chern, in his very famous paper, published in 1946, is about developing Chern classes. And these are the classes most fundamental for fiber bundle. So all these are using curvature and everything. And the first group developed the concept of characteristic classes, which attach to each gauge field some vector bundle, some integer cohomology classes. And these classes turns out to be fundamental global invariant of physics of gauge field theory. And they appear in high-energy physics, condensed matter, and many related fields, as we know. Of course, it's fundamental in geometry. Actually, already in 1947, Weyl suggests that this integral class should be fundamental tools to study quantum gauge theory, to be a tool to quantize physics. This vague suggestion turned out to be accurate and fruitful. And so it was not until 1954 physicists start to understand this could be useful for other things. Yang and Mills attempt to study the isospin doublet of protons and neutrons based on SU2 gauge theory. But the physical theory was criticized by Pauli. He said the quanta in the gauge theory cannot have mass due to gauge invariance. So he has to wait until 1960s on the concept of spontaneous symmetry breaking, and the Higgs mechanism was initiated by several people, of course Higgs, and then Graustein number, and several other people. And then after that, we know particles were allowed to acquire mass. But there's still a very important problem that to deal with nature. So it was in late 60s, and Graustein, Salam, Hilbert introduced the electric wave theory based on the gauge group, which is U1 times SU2. And later it was found that strong force is also dictated by gauge theory with gauge group SU3. All these are extremely important, and in the 1970s, Gross, Polacek, and Wilczek has discovered the strong interaction has asymptotic freedom. And this becomes the foundation of the theory of quantum chromodynamics. So both weak theory, electromagnetism, and strong theory is united, and this is called the standard model in high-energy physics in the 1970s. This is probably one of the most successful theory of nature, which is a combination of huge amount of work, including physicists and mathematicians. But before physicists universally accept this theory to be sound, they have to know that quantum theory and gauge theory are renormalizable because there are too many infinities appear in the theory. They have to give a reason to it. So this was achieved by Tuhov and Riemann, who got a Nobel Prize because of that, based on the gauge theory of Fedor, Popov, and also Feynman. So this is a spectacular development, gauge theory, which also can go back to Einstein's theory after the development of that. But at the same time, when Hammermeyer started the invention of gauge theory in 1919, another mathematician called Kaluza, and he's a mathematician, and he proposed a very original idea to merge gravity with electromagnetism. And this is called dimension reduction. He proposed to study 5-dimensional pure gravity that's invariant under circle symmetry. And this is rather spectacular. Each time I look at it, I still find it spectacular. So you look at a 5-dimensional theory with no matter whatsoever. It's a pure gravity with no matter, and yet the effective theory, after you cozen down by circle, start to get gravity plus electromagnetism. So matter come out from nowhere. It's a miracle. You found matter out of nowhere. And this actually was very pleasing to Einstein. Einstein was very surprised and appreciated this theory very much because it's such a beautiful theory. I always found it beautiful up to now that out of vacuum you create something natural and interesting. But there's one thing that was found, namely there's extrascalar field, which was not created in nature. So despite it's beautiful, it cannot be used as a fundamental theory. So it was abandoned. But it's so beautiful, this idea of dimensional reduction keeps on coming back. And so all the way up to now. And actually, the modern version is something to do with Calabi compact equation, where we simply replace a circle by 6-dimensional compact manifold. That means something called supersymmetry. So the existence of such space was found by me in 1976. And actually, at that time, nobody in physics thinks that is any interesting whatsoever. And in 1980, I have the opportunity to have several postdocs. One is Gary Horowitz, who was my postdoc at the time in Princeton. And also Andy Strominger was a postdoc there. And I insist them to look into this. They insist to refuse to look into it. It is not Lorentzian signature is wrong. There's no interest to look at it. So until 1984, when string theory start, and they start to be excited about it. And this has been a very important change for mathematics. Because since then, many more people, physicists especially, was very excited about this whole theory. And this whole theory has been fundamentally changed many important developments in mathematics itself. And we hope that it also creates something important for physics. And this has been influential, including my work with Ken Runberg and Donaldson on the Hermitian-Yang-Mills equation and many subjects. And this has been really important for mathematics because it does tell you something important that solves some old problems in mathematics, independent whether string theory is right or wrong. So in between of this famous work and Yang-Mills and Hammond-White, there's also famous experiment demonstrate the holonomic phenomenon in gauge theory. This concept of holonomic behavior is very interesting for mathematics. That actually was discovered long ago in Relativity and earlier works. This is a concept of parallelism. So I think starting from old days when Einstein was led by geometers, Minkowski, Riemann, Ritchie, and Hilbert to use symmetry or space-time to show the true nature of gravity is geometry. It was a true revelation to physicists. But when Hammond-White and others demonstrated nature of matter beyond gravity come from geometry of fiber bundle, it is equally spectacular revolution. It also influenced mathematics in a strong manner. But now the remaining question, of course, is how to unify gravity with other matters. And perhaps it's through geometry again. And we hope that some idea from Kaluza-Klein mechanism could play a role. But in any case, I think a new concept of geometry is needed. And perhaps we can call it to be quantum geometry. And this probably, I won't be able to see it, but I hope some of you can do it. But this will take a huge amount of work, not only by geometers, by physicists, by many people, by experimentalists, presumably. So, but I hope it can be accomplished. I hope I can see it before I die. Thank you.
I'm asked to have a dialogue with Professor Yao, and mostly I'm going to ask questions so that he have a chance to further explain some of the points you made. So thank you, Professor Yao. Let me just focus on where your contributions come in, okay? You're best known for Calabi Yao. Certainly to physicists, that's one of the best known things. And in order, our dream of the final theory for physics is string theory. Yeah. And for string theory to realize nature, we have to go through Calabi Yao manifold. So that's the path for us taking, and many of physicists are working on that. My question is, okay, when you are trying to work on Calabi's conjecture, can you comment on the process, what happened? And I assume that you're not thinking about physics, or you're thinking about Einstein equation. So.
Yeah, I actually was thinking about Einstein equation. I remember I was in Berkeley when the first time I looked at this whole thing. I took a course, I didn't take a course, I ordered a course in general relativity. I looked at all these equations, Schwarzschild, K, and all that. They all have some singularity. And they're vacuum, no matter. So I'm curious, I said, does there exist a non-singular solution which is vacuum and has gravity, where it's non-trivial? I didn't know how to construct such a thing. So one day I was in the library, I looked up in the books, I found Calabi has made a conjecture, but in a much more restrictive class of manifolds, namely Kähler manifold. And from there, I can find many examples that answers those questions that I mentioned. So I got very excited about it. So in a way, I was motivated by general relativity. But once I look at Calabi's conjecture, I pay every attention to the mathematics part. The first reaction is that I could not find a single example, even more general than Caylor manifold. How the hell that Calabi can believe that you found many, many of them systematically? So when I start to work on it, I'm working in a direction that is wrong to find counterexample. But many of my friends, including Nigel Hitchen, who is now very famous, we all were in the Institute for Advanced Study, young guys, and we say that, well, let's try to give a counterexample to this Calabi conjecture, which is simply too good to be true. And many people continue to work it, and so am I. But I insist to charge on. Some of them get discouraged when they could not do anything. But I decided that one way or the other, we have to solve this problem, because this is really a cornerstone for understanding Ricci curvature for space. And so I insist on working it, and as in 1973, I even announced I found a counterexample. And I got so famous, actually, at that time by finding the counterexample in a great, big international conference in Stanford. But to my great embarrassment, after 2 months, when Calabi wrote me a letter, I found that what I thought to be a counterexample does not hold anymore.
I hope you didn't publish that.
Well, actually, the counterexample is worthwhile to be published. Some people publish it when I did not publish it. It's actually an interesting example in the algebraic geometry. But anyway, so, well, I did not publish it, but I feel so embarrassed because it was announced in a big conference in Stanford, and Chen, who was the organizer, chairman of that conference, announced this is the best work done in this conference. So I spent about 2 weeks, day and night, trying to give further counterexample. Each time I tried to produce a counterexample, it broke down the argument. So I decided something must be wrong. Namely, I was going in the wrong direction. So only after that, only the hardship, I decided that this is wrong direction. Without going through this hardship, I probably still believe that is wrong. I mean, in fact, many of my friends, including Nigel Hitchen and many others, are still charging on to give counterexample when I turn around to try to prove it. But, you know, it's not like suddenly inspiration comes and then you solve everything. You need to build up all kind of foundation, because in those days, geometry does not know much differential equation. I have to build how to solve, you know, nonlinear partial differential equation on manifolds, and I have to do all kind of estimates and all that. That takes me 3 more years to finish. So that was very rewardable when I finished it. So I finally understand Ricci curvature, at least in Caylor manifold. And then most important application at that time was for algebraic geometry. You know, in the process, 3 years when I tried to give counterexample, I found many ways to show that if Calabi conjecture were right, then there's some consequence. Then we want to show this consequence wrong. That's how you prove counterexample, right? So once I prove it, then all these consequences I thought too good to be true is now all right. It all becomes theorems. So the effort to give counterexample turns out not waste. So the very first thing is actually when Mumford, right after I proved the Calabi conjecture, Mumford come to visit UC Irvine. I took a long way.
Advisor.
Yeah, he's an advisor. I took a long way. I drove about 3 hours one way. I just got married, actually. And I drove 3 hours, go to listen to Mumford. And he was giving a talk and in completely different subject, in algebraic geometry. He said, oh, this is a famous problem, and this has not been solved, and Bogomolov just did this, and it's very challenging to improve it to a better number. So I was in the audience. I said, gee, this looks very familiar to me, and maybe I can do it. By the end of the lecture, I told Mumford, I think I can do it. The Mumford doesn't believe it at all, didn't believe it. I mean, I was a young guy, I was 27 years old, nothing in algebraic geometry, so he didn't think that I can do it. So I went home and I do the series calculation. I wrote it down exactly how it goes. I understand it to Munford. So Munford checked it and he was very pleased. So I solved two major conjectures in one stroke for that work. So I become much more famous in that than Calabi conjecture itself. Because there was two problems that algebraic geometry wanted to solve for a long time. So from 1976 all the way until 1984, I was basically working how to apply Calabi conjecture, the structure of it to many different subjects in algebraic geometry and differential geometry. So until 1984, when Strominger and Horowitz called me, I started to turn into this. And this becomes a very beautiful subject because, you know, at the point when they call me, Witten also called me in a matter of 2 days later. Later they work together, but at the beginning they don't work together. They want to know how many manifolds are there. And I only knew 3 at that time. I said, I knew only 3. They said, wow, this is excellent. He said, 3 now we can model.
Too many.
Yeah. we can model the universe without any effort now. They got very excited. So, and then Witten come, and then I start to develop more, and I know that I can construct many. At that point, I thought there may be about 10,000 of them. So I told them, they got very disappointed. But anyway, then it started to develop, and actually, at one point, when I arrived in Harvard, physicists thought that Calabi manifold has no use anymore. So they said, now we gave it up. And in fact, I was working with Brian Greene. You know, Brian Greene is famous now. He was my postdoc at the time. And Ginsberg looked at us. He said, these folks still work on this stupid concept. Cannot be good. And
You're talking Paul Ginsberg?
Yeah.
Or Paul Ginsberg of the archive. So.
Yeah. Anyway, but we are not discouraged. And then within a matter of few months, Brian Greene and Pesser worked out the meter symmetry. And this was spectacular. And then Candelas and several other people follow. And so in a matter of a couple of years, this whole thing led to some major development in mathematics, which solved some old problems in mathematics. And this caught people's eye in a spectacular manner. At that point, people did not pay much attention to string theory, but you know, before that, when they solved this problem, which is open, almost 100 years old, and they don't even know how to count, how to get formula to count the number of curves and all that. So when Candelas wrote down the formula, people did not believe it. In fact, there's a famous story was in 1991, I held a conference, 1990, I held a conference in MSRI in Berkeley. And there was a big debate because some of the algebraic geometers from Norway come up with come up with a number which is different from what Philip Candelas has. And the formula is clearly different. And the algebraic geometers got so pissed off by the string theory. They said, you guys just talking nonsense, total nonsense. You cannot be right. And because they said they do things, everything rigorously, guys cannot. So we were in that situation for a couple of months. And then the Norwegian mathematicians found mistake in their programming, where they use computer to do calculation. And after correct the programming, they found the number is exactly what string theory predict. It's a non-trivial number, huge number. I mean, with 15 digits, and turns out to be exactly right. So since then, algebraic geometers turned their head and start to work on this problem. And since then, there are many people work on it. So I think the whole subject is extremely useful for mathematics. But at the same time, I think we're still far away from a good understanding of Calabi manifold yet. And the classification and many important properties, computing some cohomology or many things over the manifold. I think after 10 more years, we will get much better understanding of it. I think it will be important again for string theory.
Let me make one comment and question. The comment is that we know that we want the manifold that allows string theory to describe nature.
Right.
And a group, actually more than one group physicists, do the 4-dimensional K3. Yeah. And then they ask mathematicians in their institute, is there something equivalent to 3 complex or 6 dimension?
Right.
And they were told that those didn't exist.
I see.
So it's good that Strominger and Horowitz are with you, so they know that they exist. So
Yeah,
that's where the difference of success or failure at that time. So
yeah, they didn't believe it at the beginning. And,
yeah,
but they were my postdoc. They have no
yeah,
choice.
that's why they know.
They have
it.
no choice but listen to me.
Good for them, right?
Good for them.
So can I say that the mirror symmetry actually can be treated as a quantum geometry?
Oh yeah, it's a part
So
of the
it is quantum.
It's a consequence
right,
of quantum
right,
geometry.
right.
It was something totally unexpected for mathematicians.
Right, right.
You know, from a strong coupling constant to weak coupling constant, you can solve it predictively. Many of these results actually can be proved rigorously later. But the way that it was proved was based on the formula that was inspired by string theories.
I should say, from string theory perspective,
Yeah.
mirror symmetry is intuitively obvious.
Yeah, it's
So
true.
I'm not going to put down a math because the
No,
proof is very important.
I know.
But
The
Because
thing
it's
is that it is trivial in string theory, but when it appears in the geometric representation, it's no more trivial.
yeah, very different. Right, right.
So you can relate two different subjects, one obvious, one not so obvious, is always useful.
Absolutely, absolutely. So that's actually also go back to your talk is that there should be more interaction between physicists and mathematicians.
Right.
I mean, of course, we're young, but for people who in their 40s, if they understand Chern's paper or Pendragon's work, they would have written down the Yang-Mills theory easily, right? In fact, I look at Chern's paper, he has that.
Yeah, yes, that, yeah.
But in a notation that we are not familiar with.
Well, notation is always a problem. Of course, physicists use a different notation from mathematicians, although they are the same thing. But of course, I think before 1915 or so, every mathematician are interested in physics and vice versa. But I think somehow starting quantum theory, development quantum theory, mathematicians start not to pay that much attention, except Hermann Weyl and several people like that. Because the whole subject of quantum theory is not rigorous enough for mathematicians to accept to its foundation. So mathematicians go into the wrong direction in many ways, I feel, to try to give a mathematical foundation of quantum theory. And they try and still not finish. It's probably because quantum theory is not completely right in any case. So one still needs to look
Something
for
left for the students to work on in the
right.
future. Yes,
but anyway,
right.
so as a result, they got very frustrated because they did not see a rigorous mathematics out of quantum theory. So this was kind of developed for about 50 years until in 1970s. So Atiyah Singer started to be interested in the Tuhov's theory and Polyakov's theory about instantons. The instantons was a beautiful geometry, and we got excited about it again. So then Atiyah Singer index theorem was able to use for this theory, and people start to work out many interesting work out of it, especially the famous work of Donaldson, where Yang-Mills theory was used to solve some important questions in 4-dimensional manifold. And all the topologists got excited about it because these are works that the standard topology cannot solve. Up to now, still cannot solve. And now they can use this more modern gauge theory to solve it. So this changed everybody's point of view, so starting in the 1970s. In fact, I was changed by it because I was talking with Singer. And Singer told me about, all these instantons are beautiful geometric objects. You should take a look. So I did take a look, and then I worked on it myself. I did this paper with Ken Winberg. And of course, all along, all these things are related to physics, but at the same time, they are very important for mathematics. There are many interesting ideas that come up from there and becomes important. But also at the same time, independent of gauge theory, I was working in general relativity, starting in 1973.
Oh, positive mass.
Positive mass
Yes.
conjecture.
Please.
This is also a beautiful piece of geometry that I was interested in. So this whole thing now is also developed to be rather fertile ground now. Many people work in it and create many interesting ideas in geometry. So I think, to myself, working with physicists has been very important, even just for the sake of geometry or mathematics. And they lead to many beautiful objects that I think I would not imagine before if I were working in mathematics alone. So I think in the last 40 or 50 years, it has been a very nice intertrending between physics and mathematics, and the ideas has been fruitful. The important thing is the ideas are fruitful. Yes. And once it's fruitful, many people are interested in it.
Right. So you want to say something about how you get to work on the positive mass theorem, the proof?
Well,
because that certainly starts from Einstein theory, right?
Oh, yes. So Einstein actually already thought about something called mass. As I mentioned in my slides, Einstein's theory, the classical relativity has no symmetry, no continuous symmetry. As a result, it's not easy to define the concept of mass. You see, you need a continuous symmetry, a translation to define the four vector, the mass, energy, linear momentum. And it's none, so you define something called total mass. And this is because there's some continuous symmetry at infinity. So Einstein defined it, and then he checked it for some very simple case. Then it's good, then it's positive. Why you need positive? If the thing is negative, the whole space-time will collapse because it will keep on collapsing. And then the Einstein's theory is no more stable and is no good. So we need to know the total energy of the whole system is positive. So I didn't realize this is a major problem at that time until in 1973, in the same conference I mentioned, where CERN was organizing. So Robert Garros, who is a famous physicist in general relativity, was invited to give a talk in Stanford. He put it in a way that is very understandable, a very special case of this problem into geometry. He put it down, I wrote it down, and he said, well, I challenge you, dependent geometer, to answer my question. So it was very interesting because all the geometers are there in the whole world. There are a few hundred people there. And they're watching a physicist come to tell us a problem written completely in terms of geometry, and we know nothing about it. We could not answer. So everybody was, I won't say unhappy, was awed by a question like that because we don't know how to answer. It is an actual question. So I thought about it, and I keep on thinking about it. Only after a few years, I was visiting Berkeley. After I solved the Calabi conjecture, I was working in Berkeley, working with my former student, Rick Schoen. And suddenly come across our minds some idea that we have been using. We have been discussing about this field of minimal surface for a long time. We suddenly realized that it can be done. But you just solved this very special case at the beginning. But that important case, once you solve it, you get the idea how to go on. And then, actually, no physicist believed that we can do it. Many of the relativists were my high school friends.
I see.
They said, this nonsense, mathematicians cannot solve this important problem. And nobody believes it. And then they start to call me, he said, just stop to talk about it. You cannot do it. And then my classmates. And then turns out Hawking said that it looks good. And then everybody sat up. So then there was a first stage. I mean, there are two stages of solving the thing. And then more general space-time, we were able to do it in a matter of half a year later. But physicists start to say, okay, you can do the first step. You would not be able to do the second step. So it turns out we were...
So first step is a special case.
Yes, special case, time-symmetric case. And so in fact, I visited Hawking. Hawking invited me to go to visit Cambridge. And then I talked with him for the whole day about this. And then he talked about high-dimensional positive mass conjecture. He initiated for the action principle he used, 4-dimensional positive mass conjecture. So he asked me to do it, so I finished it in half a year also. That was rather exciting because we were young. I mean, Rick Shen and I were 28, 29, and we solved the problem in a short time, and I thought it was exciting. We are energetic. We felt that there's a big challenge by the physicists, and we feel we can solve it, so we did it. And I was very happy with that, actually. So my development with physicists, I think, has been always good. And of course, once the Calabi space is important for string theory, many ideas come from physicists come in. And some of them, I must say, I was totally amazed what the idea they can bring in. Besides this meter symmetry, there are many derivatives, there are many other concepts. I mean, cyber-written come in, and written has bring in so much important concepts that it's difficult for me to imagine. And my colleague, Wafa, sometimes knows Calabi manifold better than me, and so the whole thing is very exciting, I say. Yeah.
Well, many developments are very surprising to us too.
Right.
Yeah. I mean,
but I think the cooperation is very important because Wafa is ingenious in many of these original ideas, but he did consult me each time when he put up a new idea to make sure that what he said is not nonsense. And so I'm pleased by it. Actually, talk about it during the one of the string revolution when you include the plane theory, Polchinski and all that.
Right.
So I was in Trias, there's a big conference in Trias, and Witten came and he said, well, Yao, he said, we have this idea of a plane and supersymmetric, and I don't know, he said, we are not sure whether it's good or not. So he started to explain this, what we call special Lagrangian plane now. In the old days, he called it different name, I forgot. Anyway, Becker and Strominger introduced it. So he mentioned that to me. I was in this talk, and then I went to this conference. I did not contribute much because I did not know much physics at that time, still not. So, but anyway, I learned this concept from him. So I start to think about what that means in mathematics, in geometry, and in cooperation with meter symmetry. So I started to develop what it means, a meter of the special Lagrangian plane, and came back home to Harvard and worked with my postdoc, Stasro. And then Strominger came to visit afterwards. So we started to realize this meter symmetry can be looked at in terms of geometry, which is now called SYC construction. And this SYC construction has been very important for geometry. Many important ideas was developed after that. So talking of physics has been very useful and inspiring and important for me. So, I mean, I've been working with physicists happily. In fact, I should say that when I was in the Institute for Advanced Study in 1980, when I arrived there, my colleagues are all great mathematicians. They are Borel, Harishchandra, Wei, and all this. I went there, I started to talk a lot with physicists. I talked, quite a few postdocs especially. And my colleague in mathematics said that Yao forgot to know that we have been a big fight in physicists. There was a time when the mathematician was unhappy with the dialectic case.
Oh yeah, yes.
He said, yes. I forgot that we have a big fight. Well, I said, I don't care. I mean, I just talk about scholar academic works. Right. I mean, so, but anyway, it was a happy incident.
Wang Yan left. You are the moderator. What should I do?
We are about 12 minutes beyond our allotted time, so I think maybe we can wrap up.
Okay. So, you want to say a few encouraging statements to the students? Or advice?
Okay. When I left Hong Kong, which most of you are here, in 1969, I thought I want to work out something that are interesting and important. But I don't know why, what, but I determined to do so. By the time when I solved the Calabi conjecture, I was 27. It's only 7 years after I left Hong Kong. At the time when I left Hong Kong, I actually know almost nothing in geometry. But I learned it in a short time, and I was able to do something useful and important. So I'm sure you can do the same thing. It's a question of your determination. Forget about any other things. I think the subject is so exciting and beautiful, and there's still many important works to be explored. At the time when I was working on all these things in early 70s, it was a low point for high-energy physics, for example. Many of my friends could not find a job. Despite high-energy physics, in terms of academic development, was exciting. The standard model was being built, but most of my friends could not find a job. Many of them, including the very famous YAU Shing-Tung, who was a student of Graustein. He quit high-energy physics and went into computer science. But he did great work in computer science. He got the Turing Award. So as long as you are willing to work hard and have a goal of your life, I think you will do well. That's all I can say. And it's very rewarding, I should say that, because my whole life I work hard, but I always found it rewarding to see something build up under all this effort. So I think it's an interesting thing to do.
Okay, so let's thank Professor Yao.